Well, our next presentation will be given by Dr. Gopal Kakani from the Department of Plant and Soil Science on water and bioenergy production. Thank you.
Good afternoon. I've been here for about 6 years now working on bioenergy production, so I thought I will pull in some of our data that we've been collecting on producing these crops in Oklahoma and what we have learned so far in terms of producing these crops here in Oklahoma. So just to give you why we need bioenergy, probably this curve most of us have seen, it's called as the Hubbard curve for the oil production or the reserves that we have for the world oil production. So as we see here, by 2030, 2040, we should be on that sliding down phase in terms of the amount of oil we can produce. Probably colleagues from Halliburton might be differing with this, or we might see more additions to that as we improve the processes with which we extract both natural gas and oil. We might see a shift in this curve, probably, but we might be depleting it much sooner if we shift the top of the curve. We might be hitting the total depletion of these fossil fuels pretty quickly. So there's a need to replace these fuels because we need energy. The rate at which we are consuming this energy, we need to produce more energy. So that's where the bioenergy comes into picture. And also the other one, the US imports a lot of crude. As you see in this graph here, all the way from 1992, we have reached a peak around 2008, but it's sliding down since then. What are the reasons for that? This is due to increased crude and natural gas production within the United States and reduced petroleum oil consumption. That's due to increased energy efficiency of the vehicles that we use and increased biofuels. I've highlighted that there. So there's an increase in the contribution of the biofuels to the total transportation fuel sector. So right now, the bioenergy contributes to about 9 to 10% of the total energy needs in the United States. And also more of renewable power, wind and solar. And also a weak economy where we are not been consuming that much of the transportation fuels as we did when the economy was much stronger. So these are some of the criteria for decrease in the recent years of the US imports of crude oil and petroleum products. So that's where again, the bioenergy is essential for meeting the energy demands. And the other case is quite obvious, the climate change that we are seeing, or we are experiencing it. As I show here, the top left graph, this is the CO2 concentrations in the atmosphere starting about 800,000 years ago. These have been dug out from the ice cores in Antarctica. As we see in the past, the cycles of up and down have been there. So the max we have reached is about 280 or 270 ppm of carbon dioxide concentration in the atmosphere. And we dip down to say about 180, 170, depending on the climate that's prevalent during that time. So it's warming and cooling trends that will determine the amount of carbon dioxide in the atmosphere. But what's happening recently is right now we have crossed close to about 400 ppm. So just last month, we have even reached about 402 ppm for about a week. So that's the highest concentration of carbon dioxide in the atmosphere that's been recorded so far since we started measuring the carbon dioxide in the atmosphere. So we have this Mauna Loa Observatory close to in one of the islands in Hawaii. So as we can see from 1960, that was around 315 ppm. And right now we are at about 400 ppm. So this 80 ppm decrease or increase in carbon dioxide in the atmosphere, it's mostly attributed to the burning of fossil fuels. That's the petroleum and crude oil products. So it's essential that we reduce this concentration in the atmosphere because it's going to have a tremendous impact on the temperature, as we have already seen that. For example, in India, 2 weeks back, the temperatures were around 85, 86 degree Fahrenheit. But within 2 weeks, they've shot up to 103 and 104. So these intense events within a short period of time are going to happen much more frequently if we don't contain this carbon dioxide in the atmosphere. And obviously, it has an impact on the water cycle. The change in temperature, the change in CO2 concentration. This is going to create changes in the global water cycle. So who receives how much when would be modified by this increase in CO2 concentration and also increase in the temperature. So one of the points I wanted to highlight from the recent Intergovernmental Panel on Climate Change, their 2013 or the 5th assessment report. Say, for example, because we lie in the mid-latitudes and subtropical dry regions, mean precipitation will likely decrease by end of the century in the mid-latitudes and subtropical dry regions. So even though some of us may not be here, but the future generations need to face this decrease in precipitation and also a likely increase in temperature along with the decrease in precipitation. So that's a double whammy for those who will be living in those times. Okay? And also there'll be other changes. So the monsoons would shift and also they'll weaken, and lots of things are going to happen if we don't contain the CO2 concentration in the atmosphere. Okay. So again, why bioenergy? I think most of you are watching this Cosmos off late. The 3rd episode was on yesterday. I grew up when I was going to school. I used to watch this Cosmos back in India. I was very fascinated with that show, and when it started again, I got hooked up to that. But one thing I noticed, like the picture I show here, you see the green tinge on the surface. That's Carl Sagan when he was giving that first episode lecture on that. And this is Neil deGrasse Tyson in 2014, the latest episode, the first episode. We can see the shift in the greenness of the same location. This is in the Northern California region. So this is much greener here when he shot that in 1979, 1980. And this was shot, I think, probably 2012 and 2013. So there's a shift in the landscape that we're already seeing because of this climate change and variability that's happening. Okay? So that's why we need this bioenergy. So why do we need, and these are all the different options we have to produce bioenergy. So we have lignocellulosic crops like switchgrass and energy sorghum. Then we have oilseed crops. Right now we use soybeans, but again we have other alternative crops like camelina. And we have sugar crops, for example, energy beets or sugar beets that we can produce here in the United States, along with sugarcane and other sugar-based crops. And we also have large portions of this conservation reserve program. At the end of the season, there's lots of biomass that's available on these CRP lands that can be put to use for producing these either bioenergy or biofuels. And on top of these, we should be more concerned about the sustainability of the planet as we produce more energy. Or as we need more energy, it's essential that we produce that in a sustainable fashion. So our bioenergy program, it also looks at the overall sustainability of producing these different feedstocks. And this is what is mandated in the Energy Independence and Security Act. By end of 2025, we should be able to meet at least 30% of the total transportation or the fuel requirements through biofuels. And we are already doing that to some extent, like about 15 billion gallons right now is produced through corn ethanol. And on top of that, we are adding a little bit through these blue squares here on the top. They are the biodiesel production. That's close to about 0.7 to a billion gallons right now. And there is potential to increase through cellulosic biofuels, those blue bars there. That's through cellulosic biofuels and other advanced biofuels, such as through algae, and also biomass-based diesel production. So some of the breeders and geneticists are working to produce oils, say in switchgrass and sorghum plants, so that we could directly extract the oils from the plant biomass rather than from the seed, because you have a lot more plant mass to store the oils in the plant compared to the seed material, which is smaller in size. So there's a lot of effort that's being put into improving both the traits and also the species to produce these different advanced biofuels. And coming to the water, because to produce all this, we need water. So I just wanted to give a glimpse of how much of water we use, say, to produce different products. Say, for example, a can of fruit, we need about 9.3 gallons of water. Say, for example, to produce one Sunday newspaper, we need about 150 gallons of water. So there's a lot of water that we use that we don't know that we are actually using. When we read a newspaper, it costs about 150 gallons of water. So there's a lot of water need for each and every process that goes into the production of these various products. And when we look at, say, coming back to the energy, these are the different fuel types. Say, on the top you have natural gas. That's one of the least water consuming industries right now, production and transportation of the natural gas. And then we have the coal mining, coal, and the uranium mining and enrichment, the oil that we are producing, either it be from oil sands or from other sources. So they are on the higher side of water consumption. So that's close to about 80 to 100 gallons per million BTUs of energy that's produced. Compared to that, say, corn ethanol is a little bit expensive in terms of water use. So that's close to about 1,000 gallons of water for the million BTUs that's produced from corn ethanol. But whereas cellulosic ethanol or the advanced biofuels, again, would fall in line with that of the current water requirements by the oil industry. So any oil that we can replace would help us use that water for producing these advanced biofuels. So there is a potential trade-off between producing cellulosic biofuels and reducing the amount of water or consumption of the petroleum products. Okay. And this is another in a different study where they did some life cycle analysis of these different energy scenarios. So this is again for corn ethanol. We need about 11 to 160 gallons per gallon of ethanol that's produced. So it depends by the region because it's hot, dry, or wet, and also the soil types. The amount of water that soil can hold would determine the amount of water that we are supplying to the crop. So there's a lot of variability in the amount of water that's needed to produce a gallon of ethanol from corn. Say, for example, but if you are going for switchgrass ethanol, because that's one of the least water consuming crops, so it's about 1.9 to 4.6 gallons per gallon of ethanol that's produced. So among all the energy sources that we see, production of ethanol from switchgrass requires the least amount of water to produce the same amount of energy. So that's how we would see the effect of bioenergy, both in terms of producing energy and also save the water resources as we improve our technologies to produce more of these advanced biofuels. And coming back to Oklahoma, we have been doing studies over the past 5 years, spread across the state all the way from Goodwell in the Panhandle, Woodward, Stillwater, Chickasha, Lane, and Ardmore. We have got a suite of experiments ongoing to study the amount of biomass we can produce, because our objective here was to produce them without any irrigation, just using rainwater. So, and as we can see in the bottom graph, this is the gradient in the rainfall across the state and also in the temperature. So that determines the amount of water that's available, and the temperature would determine the amount of water that would be needed to maintain the crop under those conditions. So I'll show you some variation. This is the variation we see in the rainfall. So these graphs at these various locations, say for example, Goodwell, the average rainfall is about 12 to 15 inches per year. But whereas when we come to Lane, that's close to 45 to 50 inches of rainfall. So there's a lot of variation within the state that we can exploit to produce these bioenergy crops and make use of the water that's available through rainfall. And this is the actual crop production figures. These numbers are not published yet. This is the first time I'm releasing out to the crowd here. So as you can see, the variation in the amount of biomass that we produce. We have 3 different species that we call, say, mixed grasses. That's a mix of native grasses, switchgrass, Indian grass, and big blue stem that are native to the region here. And then we have sorghum. This is the high biomass sorghum, or the forage sorghum. And then we have switchgrass. So these are 3 species that we have been studying being native to this region. And as you can see, the bars here, they represent different years. Different colored graphs represent different years. And sometimes, in some of the years, the bars totally disappear, depending on the type of species. And what we have observed is sorghum, it's very sensitive to the, even though it's called as a drought-tolerant crop of its origin in Africa, even that cannot sustain the dry periods like that we have seen in 2011 and 2012. So it'll succumb to those dry periods of extended periods, more than 4 weeks of dry period. So that's what happened at Chickasha in, say, 2011. Again, sorghum at Lane, 2011. So that's what we see, these red bars that are dipping down in 2011. But whereas the native grasses, being perennial in nature, they have the flexibility to adjust themselves to the amount of soil moisture or rainfall that's being received in that particular region. So we see that most of these mixed grasses and switch grasses, even though there is a decrease in yield, there is what I would call these crops as minimum guarantee crops. You could at least harvest some biomass if you're going on a large scale for these bioenergy plants in this region. And we've also looked at the water used by these crops. So that's important, because even though we are not irrigating, the water that's coming from the sky can be put to other uses, say used by industry or used for drinking purposes or for recreation purposes. So we also monitor the amount of water that these crops are using. And roughly that adds to about anywhere from 400 to 600 millimeters of water during the entire crop life cycle. So these switchgrass and sorghums that we are growing here use anywhere from 400 to 600 millimeters of water. But the important thing is looking at the ecosystem efficiency, because when we are using water, we are producing a product, right? That's the plant biomass that we are producing. The efficiency of converting or using this water to produce biomass, we also monitored that. And both of these species, switchgrass and sorghum, are almost similar in their performance for the ecosystem level water use efficiency. So that's the amount of carbon dioxide that we are trapping or capturing from the atmosphere for each millimeter of water that's transpired by these crops, or lost through evapotranspiration from these crops. And when we compare this with other ecosystems, say grasslands, native grasslands, or crops, or deciduous broadleaf forests, they obviously stand out in terms of their ecosystem level water use efficiency. For example, the grasslands, native grasslands, about 3.4, 3.5, compared to about 12 to 14 of the switchgrass and forage sorghum ecosystems. So the advantages are quite evident in terms of the amount of carbon dioxide that we can pull from the atmosphere by growing these energy crops. And obviously one of the things is this carbon is always recycled. Unlike the fossil fuels that we are digging from the ground and pumping them into the air, the CO2 that we are capturing through these feedstocks can be used to produce fuels, and once it's back into the atmosphere, it's again taken by the bioenergy crops that we are producing. So it's a continuous cycle where we capture and release the CO2. But along with that, we also want to look at what other impacts this is having. So we have another project that's looking at the environmental impacts. What this study shows is that when we convert, say, marginal croplands or grasslands to switchgrass production, obviously there are some costs because you're producing more biomass than what was being produced earlier on those systems. So some of these studies show that there'll be an increase in the water use by these crops, anywhere from about, say, 3 to 20 or 30 depending on the type of conversion that we are looking at. So the scenario 1 here is when you convert marginal cropland to switchgrass production, whereas scenario 2 is grasslands to switchgrass production. But again, they have their benefits in terms of reducing the sediments that's moving into these streams. So that's an important concern when we are looking at the stream flow of water. So growing these bioenergy crops also has an advantage in terms of reducing the amount of erosion, in turn moving the sediments into the streams. Okay. So that's in a nutshell what we've been doing here in terms of trying to understand whether this would fit into the overall energy scenario, and at the same time provide some environmental benefits in terms of both water use and also reduction in the atmospheric CO2 concentrations. And thank you. And these are some things for you to take in terms of where is all the water, in terms of where it is. So oceans, glaciers, aquifers, lakes, and rivers. The amount that's in the biosphere, say the plants, animals, that's very minute compared to the water that we have out in the oceans there. And we are also losing water naturally. So the water in the oceans, we lose that on an annual basis. Say, as I show here on the bottom, about 10 to the 5 times that much of water in cubic meters is lost every year. So it goes into the atmosphere and it's again broken down into hydrogen and oxygen. But that's constantly replaced by the geological processes. So that's why we haven't lost, or the planet hasn't dried up so far, even though we lose the water on that scale. Any questions or thoughts?
So a few years back, there was some concern about how producing the biofuels consumed as much or more fossil fuels than the end product would replace. What's the status on that now?
I think that came in mostly because in terms of the amount of fertilizer inputs, that's where you would use the fossil fuel, say the natural gas that's used to produce the fertilizers or the nitrogen fertilizers. So you'll have some energy inputs, obviously, because plants need nitrogen to grow. But compared to other crops, most of the studies have shown that there is a 1:5 ratio input to output. So for every 1 input of energy, you would get 5 units of output when you're going with these advanced feedstocks like switchgrass and forage sorghum, because the nitrogen inputs are much less.
Okay. Does that 1 to 5 account for just fertilizer or fertilizer as well as the fossil fuels the equipment would use?
That's in total, everything put together.
Well, thank you very much.
Thank you.